Section 15.4, using polar coordinates for integration. So if you just remember right triangle trigonometry, or just draw a right triangle with x, y, and r as the sides, then some formulas that we're going to be using are x squared plus y squared equals r squared. And then have this as the angle theta. And then x is equal to r times cosine of theta. Y is equal to r times sine of theta. And these two just come from saying cosine is adjacent over hypotenuse, and then solve for x. Sine is opposite over hypotenuse, and then solve for y. And then you could also do tangent. Y over x is equal to tangent of theta. So I like to write them like this. So all of the x and y information is on the left, and all of the polar information, r and theta, is on the right. So when you're integrating with x's and y's, you could have some function with x's and y's, and then it's going to be over some region, r, and then right here you can put dx or dy. You could also put dy or dx. So the choice is yours. At the end, you'll end up with the same thing, even if you switch the order. Now, if you're doing that same integral, but you decide using x's and y's is probably not the best way to do it. So I'm going to change it over to polar coordinates. And this is something we actually do quite a bit. There's quite a few times when the original integral is just too challenging, and you change it over to polar, and suddenly it's easy. So then you would need to change, using these formulas over here, you would need to change the function into a function of r and theta. And when you change to polar, there is an extra r that you need to multiply by. So if we were in class and doing the full lecture, I would give you the 15-minute explanation of where this r comes from. It's beautiful, but we're doing condensed math right now. And then dA. And because we are now working with r and theta, then dA, you can either do the order dr, d theta, and then that's the way it's usually done. But if you want to switch them, you can. You can go the d theta first, and then dr. Okay, so don't forget, when you switch over to polar, there's this extra r that you need to multiply by. Then, for an example. So before we get to the example, let me just show you real quick. If you were going to integrate x squared plus y squared inside of a radical, which means this is a circle, and then somebody took the square root, or it was a sphere, and then they solved for z and they got this. So how do you integrate that? Going back to Math 3b. So perhaps you remember trig substitution, but watch, in polar form, x squared plus y squared is equal to r squared. Then put the extra r, and then dr, d theta. And then this just becomes r. So that means there's r times r, so you're just integrating r squared. And then integrating with respect to r means that it's r cubed over 3. And then you would integrate with respect to theta. And in less than a minute, I was able to integrate this. Where if we were back in Math 3b trying to do this one, we would still be working on it for the next 10 or 15 minutes. So that's part of the point of polar. Now on to the official example number 1. R is equal to sine of 2 theta. So first of all, this is a function in 2 dimensions. It doesn't say z. So we could actually graph this. I'll need to change the mode. It's in radians, that's good news. Go to polar, and then graph sine of 2 theta. Change the window to go from 0 to 2 pi, so we can see the whole thing. And the biggest that sine gets is 1, so this can range from -1 to 1. The y's can range from -1 to 1. And then take a look at the graph. So it makes this pretty little flower right here. Or perhaps it's a butterfly, the 2 wings of the butterfly. Anyway, now find the area in total. So there's 1, 2, 3, 4 petals on this flower. So if I could find the area of just one of them and then multiply by 4, that might cut down the work. So if this is 0 to 2 pi, if I cut that in half, that would be 0 to pi. And then if I cut that in half, it would be pi over 2. So I think if I go from 0 to pi over 2, then yes, it graphs just one of those. So for this, find the area enclosed by the 4 petals. It's actually called a rose. Anyway, find the area enclosed by all 4 of those. So that means that we're going to do a double integral, and then it's just going to be r dr d theta. So there's no extra function in here, because if you put an extra function in here, then you're finding volume. With this, we're just finding area. And this says we're going to go ahead and integrate with respect to r first of all. So we have to see what's the smallest that r gets and what's the biggest that r gets. So the r is measured from the origin, and the smallest it would get is right there when it touches the origin. So that would be 0. And then at some point, the r would go out here in order to graph that point. And that means that r is equal to sine of 2 theta. And then going from 0 to pi over 2 graphs 1 petal of it. So the theta will go from 0 to pi over 2. And then as we saw, there was actually 4 petals, so multiply by 4. Now go ahead and integrate r with respect to r. So that's going to be r squared over 2, evaluated from 0 to sine of 2 theta. And then later d theta, integrating from 0 to pi over 2, and still multiply by 4. So when you substitute this in, it's going to be sine squared of 2 theta over 2, and then this will be 0. So it's sine squared of 2 theta over 2 when you substitute this limit in, and then minus 0. Now we need to integrate sine squared. And hopefully from Math 3B, remember the trig identity. In order to integrate sine squared, you need to use 1 minus cosine, and then you double the angle, and then that is over 2. Now that's the formula for this. So with this 2, I'm just going to move it over here, factor it out. So then Oh, I could even move this 2 out here, so that would mean that the 4 gets divided by 4. And then do the antiderivative. So that's going to be theta. The antiderivative of cosine is sine of 4 theta. And then because of the chain rule, we need to divide by 4. And then all of this gets evaluated from 0 to pi over 2. So let's see, you substitute a pi over 2. And then when you substitute the pi over 2 here, that's going to be sine of 2 theta, which is 0. And then substitute the 0, so that's 0. And the sine of 0 is also 0. So the only thing left is pi over 2. All right, now we're going to find volume. So if you're given some function, a function of r and theta over a region, which is going to be called r, then the volume is equal to the double integral over that region. Then you need to put the function right here. Then there's that extra r, and then dr d theta. And because you have one dimension times a second times a third, then that's finding volume. So for example number 2, how about if the function is a nice simple x minus y, and then it's over this region right here, which is a quarter of a circle where the radius is 2. So that's r. So basically that's saying you're walking around the xy plane just in this quarter circle, and as you walk around you look up to the function, or perhaps part of the function's underground, and you calculate all the volume above ground and below ground. Above ground will count as positive volume, below will be negative volume. And because we're just integrating, then it's going to, positive and negative will cancel each other out. So we need to, first of all, change this to polar. So in place of x, use r cosine of theta. In place of y, use r sine of theta. For a circle, you could use x squared plus y squared equals the radius squared. But if you change this to polar form, x squared plus y squared equals r squared. Or in other words, r equals 2. So it's much easier to use this function, r equals 2, than it is to use x's and y's. Okay, so it's going to be, the total volume is going to be integrate and integrate, and then it's x minus y, so that's going to be r cosine of theta minus r sine of theta. And then there's the extra r, and then dr d theta. So I always prefer to just use dr d theta. I've never or rarely found a time when it's advantageous to switch those, but you can switch them if you want to. And then what are the limits for r? So r at the very smallest would be 0 at the origin. And then r would go out here, and then the very biggest it gets is when it reaches right there. And then that's going to be when r equals 2. So the limits for r are going to be 0 to 2. And then this angle would be 0, and this angle would be pi over 2. All right, Now, I think what we should do is, this has r, each of these has an r, so we could factor that out, put it together with this r, and it'll make r squared. So just do that little bit of algebra first. So in the parentheses, it leaves cosine minus sine, and then there's going to be r squared, and then the dr d theta. Now we're integrating with respect to r, so this part's going to become r cubed over 3. And then r cubed over 3 gets evaluated from 0 to 2. And then later we'll do the d theta. And then so when you substitute a 2, this is going to be 8/3. And then this will be minus 0. So it just leaves an 8/3. And then that 8/3, you could factor it out. And then integrate cosine of theta minus sine of theta. So it's 8/3, and then the antiderivative for cosine is going to be sine of theta. And the antiderivative of negative sine is positive cosine. And then evaluate from 0 to pi over 2. So there's 8/3, which is factored out. And then it's going to be sine of pi over 2 plus cosine of pi over 2. Minus sine of 0, oops, that's a 0. And then if you distribute the minus, minus cosine of 0. I keep writing thetas at 0. So let's see, sine of pi over 2, that's a 1. Cosine of pi over 2, that's a 0. Sine of 0 is 0. And cosine of 0 is 1, but it's got this, so it's minus 1. So that is 0, because the 1 and the negative 1 are going to cancel, so it equals 0. And then let's take a look at the graph and see why is it that the answer is 0. So first of all, here's the function z equals x minus y. And you'll see that it's a plane. Some of it's above ground and some of it's below ground. And it's symmetric because there's no extra number in front of x or an extra number in front of y. Whatever is above ground, the same thing is mirrored below ground. And then if you look at x squared plus y squared equals 4, so that makes this cylinder. And if you look right here, then that part is going to be positive volume. And if you look down here, that part is symmetric, and this positive volume and this negative volume, they cancel each other out, so you get 0. Okay, now on to the next example, number 3. Evaluate this integral over the region R, and the function is going to be y squared over x squared plus y squared, and then dx dy or dy dx. And for the region, it's a donut. So make one circle that has a radius of 3, and make one circle that has a radius of 5, and then shade the area in between them, and that is how you make a donut. Okay, so as we saw before, with circles, it's very easy to use radians, because this one is going to be r equals 5, and this inner circle is going to be r equals 3. Now we also need to change this to radians, so x squared plus y squared can be replaced with r squared. And on the top, y is equal to r times sine of theta. And I almost forgot the extra r, and then dr d theta. So the limits for r are going to be from 3 to 5. And because it goes all the way around the circle, that means the angle is going to be 0 to 2 pi. So this is going to have an r squared, which is going to cancel this r squared. So all that remains is this r. So there is a sine squared of theta, and then there's just this single r. Now let me show you a little thing that some people like to do. So this is the r information, and this is the theta information. And because they're separated with multiplication, then you can separate this into two integrals. One is going to be for the theta information, integrate sine squared of theta d theta. And then bring down this multiplication, multiply with the integral from 3 to 5 of r dr. So that way, we basically can work on each of these at the same time and then multiply them. And because that's multiply, it's going to be the same thing. So in order to integrate sine squared, we need the identity that it's 1 minus cosine of 2 theta over 2. And then for this one, we could go ahead and integrate. So that's going to be r squared over 2 being evaluated from 3 to 5. And for this, I would like to factor out the 1/2 and then integrate the 1, so that's theta. Integrate the cosine, so the negative sign will stay there, and then it's going to be sine of 2 theta divided by 2. And that gets evaluated from 0 to 2 pi. And then for this one, so you substitute the 5, that's going to be 25 halves minus 3 halves. I think I have just enough paper over here to finish the problem. So there's going to be the 1/2, and then this will be 2 pi. And then when you substitute 2 pi in here, sine of 4 pi is 0. When you put the 0, that's 0, and sine of 0 is 0. So the only thing that remains is the 1/2 times the 2 pi. And then as far as these guys, they've already got a common denominator. Oh, I forgot to square the 3. So it should have been 3 squared, or 9 halves. So this is going to be 25 halves minus 9 halves. That's going to be 16 halves. And then finally, these 2's will cancel, so that's just going to leave pi, and this is 8. So the final answer is 8 pi. You're right, we should do another one. So here's the last one for this section. Example number 4. and that is just set up the integral. So there's times in applications like physics and engineering and stuff like that when you need to calculate something, but before you could tell the machine, here, integrate this for me, well, you have to set up the integral. So this one is, find the volume between two objects. So find the volume between x squared plus y squared plus z squared is equal to 100, and 3x squared plus 3y squared plus z squared is equal to 9. So this first one right here, that's a sphere with a radius of 10. So it looks like that. And then this one is an ellipsoid, and so it would look sort of like, I don't know, it looks like a capsule, like Advil or something like that. So anyway, then find the volume that's between them. So first thing is change to polar form. So we know that x squared plus y squared is equal to r squared. With those formulas from the beginning of this section, it doesn't say anything about z, so the z is just going to have to stay there. So x squared plus y squared, that's going to be r squared. So that is the equation for the sphere. Then we need to solve for z. So z is going to be 100 minus r squared, and then take the square root of that. With this one, you could factor out the 3 right here, and it would then leave x squared plus y squared. So that one has 3, and then replace x squared plus y squared with r squared. And then it would have plus the z squared equals 9. And then also solve for z. So that would be 9 minus 3r squared. And then to get rid of the square, take the square root of both sides. Okay, now this is a lovely picture, but it doesn't really help me set up the integral. So if you look in just the first octant where x, y, and z are positive, so just right here in this corner. So this one is a sphere, radius is 10, so up here 10, here 10, here 10, and then it would swoop down like this, like a circle, and swoop down like this like a circle, and it would also hit the ground like a circle. And for this one, if you let x and y both equal 0, then z is equal to a 3. If you let y and z equal 0, and then you solve for x, it's going to be the square root of 3. And likewise, if you let z and x equal 0 and you solve for y, that's also going to be the square root of 3. And then it's got a rounded circular shape like that. It goes like this. All right, now set up the integral. So it's going to be a double integral. And right now I'm only using the first octant. So there would be, well, as the name octant implies, there's 8 of these. So there would be this side, the right side, behind it, and on this side. And there would also be underground, there would be 4 of them. So in total, there's 8 of them. And they're symmetric, so I can just calculate one of them and then multiply by 8. And then we need the function. So for the function, basically we are calculating all of this volume that's between them. So what we're really doing is integrating this function, the sphere, finding the volume under the sphere, and then if we could just control the radius, instead of the radius going from the center all the way out, but we can control the radius to go from here to here, then that's going to find us the volume. So it's this function that we are integrating, 100 minus r squared. Then of course there's the extra r and everybody's friends, dr and d theta. And then r goes from what to what? So the smallest that r gets is when it's touching this function. So when it's touching this function, that's this thing. So the smallest that r gets is the square root of 9 minus 3r squared. And then the biggest that it gets is when it's equal to 10 out here. So with this one, I can't just use a number because, for example, when it's right here, that means r is a 3, and then it's going from 3 to 10. Well, when it's right here, then it's going from the square root of 3 to 10. So this can't just be a number. This has to be a function because as you go along, this is changing the length of r. So when r goes from here to here, it's a 3, but when it goes from here to here, it's a radical 3. So it's changing all along this. So you need a function right there. But out here, this is just a sphere and the radius is always 10. So for this limit, you can just use a 10. And then for the angle going from the x-axis to the y-axis, that is 90 degrees or 0 to pi over 2. Actually, that one would not be too bad to integrate, but the direction said just set it up. So that means that we're done.